In this video, we will discuss geometric operations. We will cover geometric operations, scaling, translation, rotation. We will show the one-channel representation, but unless specified, we can apply these operations to each channel simultaneously. We will treat the image as a function of y and x. Y is the vertical direction. X is the horizontal direction. Although x and y are real numbers, we will sample integer points of x and y. For example, 0.00 or 0.11. In a geometric transformation, we change the coordinates of the image x and y. The new image g is a function of x prime and y negative prime. G and x prime and y prime has the value of f corresponding to the values that have been mapped from x and y. We will deal with a subset of geometric transformations called affine transformations. Scaling is where we reshape the image. We can shrink or expand the image in a horizontal and or vertical direction, shrinking the image or making the image larger. We can scale the image along the x-axis. Let us use a to represent the scaling factor. We can scale the image by 2. G of y and 2x is equal to f of y and x. Hence, the values of the image g will look stretched relative to image f. Consider the following image. We will only work on the corner pixels points. Consider the image at 0.00. The x-coordinate is in red. Applying the transform, nothing happens. Here is 0.05. Applying the transform to the x-coordinate is mapped from 5 to 10 in red. Applying the transform to 0.50, nothing happens. The 0.55 is mapped to 510. Overlaying the image points, we see the image appears stretched. Let's look at the relationship between the pixel f and g. The first column of f is mapped to the first column of g. The second column of f is mapped to the third column of g. The final column of f is mapped to the following column in g. The colors shows the relation between columns of image f and g. We see several columns of g have no corresponding value in f. To determine the unknown pixel value, we use interpolation. Interpolation is where we use neighboring pixels to determine the value of an unknown pixel. In this case, we used the nearest neighbors. This just assigns the value based on the nearest pixel. There are other methods that PIL and OpenCV use. We can scale the horizontal axis. We will denote the vertical scale factor as d. Let's set d to 2. Nothing changes when applying the transform to the top portion of the image. For the 0.50, the new value after the transform is applied is mapped to 10.0. The 0.55 is mapped to 10.5. The result is the image is stretched in the horizontal direction. We can use this method to make the image larger. If the values of a or d are less than 0, the image will shrink. Translation is where we shift the image. We can shift an image horizontally by adding the number of pixels tx, then mapping the new location x prime. We can add 2 pixels. Consider the following intensity values. We can apply the transform, shifting the points. The points shift. Transforming the next set of points. Shifting the points, the image appears shifted. Let's see what happens to each pixel. We see that pixels have been shifted. Those pixels that are on the edge have been replaced by 0 values. We can increase the size of the image to include the pixels that have been shifted. We can shift the image vertically by adding pixels ty. This shifts the image vertically. We can represent a geometric transformation as a set of equations. Putting the equations in matrix form, we get the affine transformation matrix. With OpenCV, you input this matrix as an array. We also have the shear parameters. We will not cover them in this course. You can also rotate an image. We can rotate an image by an angle theta, where the red lines represent the original orientation of the horizontal and vertical axis. We can use a similar matrix to rotate an image. This rotation matrix will perform a counterclockwise rotation. The expression for the matrix is quite complex. We will simplify by assuming the isotropic scale factor r is 1. and we will rotate from the center of the image to simplify. If you make the above assumptions, libraries like PIL and OpenCV only require the parameter theta. Let's try PIL. In PIL, we can scale the image by specifying the integer number of pixels using the method resize. We can double the width of the image. We apply the method resize. The image is twice as wide. You can also shrink the image, but the input must be an integer. We can rotate the image. We use the method rotate. The input is the angle we would like to rotate the image by. Let's try OpenCV. In OpenCV, we can use the function resize to rescale the image. We scale the horizontal axis by 2 and leave the vertical axis as is. We can also specify the interpolation. The result is the image is twice as wide. The scaling factor does not have to be an integer. It can be less than 1. Translation requires the affine transformation matrix M, where Tx is the number of pixels you shift the location in the horizontal direction. Ty is the number of pixels you shift in the vertical direction. We will leave the scale factors as 1. We input the image and matrix into the function warp affine. We also input the shape of the output image. The image is shifted. There is a lot more you can do using this method. We can obtain the matrix to rotate the image using getRotationMatrix2D. This will rotate the image by angle theta. The parameter center is the center of the rotation in the source. Scale will be set to 1. Like before, we rotate the image.